Okay, so it's a great pleasure to have Philip Engel, who will give the first of his series of 2 lectures on comparing geometric and Hodge-Theoretic compactifications of moduli. Okay, so
Thanks
Philip,
so much for the invitation, and thanks for introducing me. So I want to sort of, discuss comparing geometric and Hodge-Theoretic compactifications of moduli. So I just wanted to start off with the most sort of classical case of Abelian varieties, and just begin by looking at a compact Riemann surface, sigma, or complex curve. And given such a curve, we can choose a basis of the first homology, which forms a standard symplectic basis. So sort of geometrically, we would have something like this. Some Riemann surface of genus G, and we are choosing a basis of the first homology as follows. So perhaps these blue curves are alpha 1, alpha 2 through alpha G. They don't intersect each other. And these red curves, beta 1, beta 2 through beta G, is another collection of curves that don't intersect each other. So we have the intersection product of alpha I and alpha J is 0. The intersection of beta I and beta J is 0. And the only time an alpha I intersects a beta J is when I equals J. Okay. So it's known that there's a unique basis of the space of holomorphic one-forms on the Riemann surface, such that we can, such that this basis is normalized with respect to the cycles alpha 1 through alpha G. So in particular, we can ensure that the integral of omega J against alpha I is delta ij. So 1 if I equals J and 0 otherwise. And in this basis, we have the so-called period matrix, which was introduced by Riemann. Actually, maybe it precedes him even. And we just integrate the this normalized basis of one forms against the cycles beta I. So these are these closed contour integrals. And we form a G by G matrix out of them. So the Riemann bilinear relations are that, that this matrix tau is positive definite, has positive definite imaginary part, and is a symmetric matrix. So the entries are complex numbers. And we can define the Jacobian of this Riemann surface to be the complex torus gotten by taking c to the g modulo z to the g plus tau z to the g. And so this is sort of built in such a way that integrating from a base point on the Riemann surface to a point P, the one forms omega 1 through omega g will give a well-defined point in this torus, since any two paths connecting the base point to P differ by a closed loop. And so it's natural to sort of introduce the sort of space of possibilities for what this period matrix could be. And that leads us to the definition of the Siegel upper half space, which is simply the space of symmetric G by G complex matrices for which the imaginary part is positive definite. So I'm just using this greater than 0 as shorthand. So this is just shorthand for positive definite. But there was a choice involved here, right? So we had to choose, to produce this matrix tau, we had to choose this symplectic basis of the first homology of the curve. And so it's natural to sort of quotient this Siegel upper half space by the set of such choices. Well, the set of such choices, any two symplectic bases are related by an element of the symplectic integral symplectic group sp2g of z. So this is just by definition, the matrices preserving z to the 2g with the symplectic form, which would be the cup product on the first homology. And if we sort of think of the periods, we've normalized the periods, right, so that the integral against the alpha I cycles of these one forms is delta ij. So we can sort of encode the periods against all the alpha and beta cycles by a G by 2G matrix, or I guess I've written as a 2G by G matrix, where the top half of it is the identity matrix and the bottom half is this matrix tau of periods. And then the change of basis, A, B, C, D, and sp2gz acts on this period matrix in the following way. So this is a sort of block, this is the block G by G action. And but we find that, you know, when we change basis, our one forms are no longer normalized, right, to integrate against the new alpha I cycles to be one. And so we just multiply by the inverse of the top. That changes the basis of one forms until they're normalized again. And this formula is, as I've written it, I guess I ended up with something backwards from the usual action. Maybe because, yeah, maybe people would normally consider the transpose action, but I guess it all amounts to the same thing because it's a symmetric matrix. So it's an equivalent action. All right, so how do we get an invariant of the Riemann surface? Well, we take the period matrix, but then we mod out by the choices of, so these are the choices. So this is normalized. And then this is the choices of symplectic basis. And so if we quotient the Siegel upper half space by this sp2gz action, what we get is the so-called moduli space of principally polarized Abelian varieties. So what are these? So these are, in particular, complex tori with, let's call them, let me say A, complex tori A, with a symplectic form on H lower 1 of A Z, which needs to be represented by a holomorphic line bundle. So a symplectic form on H lower 1 of AZ defines an element of H upper 2 of AZ, and we want that to be a 1-1 form. Okay, so maybe I'll just say a special, you know, it's a symplectic form satisfying an additional condition on the first homology. So now I want to sort of think about the ways that such a complex torus can degenerate. So so why do we want to do this? Well, this space AG is not compact. It's fun to compactify moduli spaces, but it's also useful. If we have a compact parameter space, then we have access to things like intersection theory and other tools, degeneration arguments, etc. So let me sort of describe degenerations of principally polarized abelian varieties. So the question is, suppose I have a punctured curve, and let me have a family X star over C star of principally polarized abelian varieties. So how can the period mapping, so there, first of all, there is a period mapping from C star to AG. We just send the point in C star to the point in AG that parameterizes the sort of this abelian variety. And I want to know, how does this period mapping degenerate? So let me sort of make a notational choice here. So, so notation, I'm just going to set, so throughout, I'm going to set T to be a local coordinate at C comma 0. So I have a coordinate on the curve C centered at the point 0. All right, so the sort of the first, major piece of information in how the period map degenerates is a certain isotropic subspace of Z to the 2G. So isotropic with respect to this symplectic form. This is the symplectic form. So this subspace is becoming distinguished in the sense that periods against its perpendicular are remaining finite. So let me give an example of this. So a classic example of, the one-dimensional example of a Abelian variety is an elliptic curve. And here's this family of elliptic curves, y squared equals x cubed plus x squared plus t. And now we're going to imagine varying the t parameter within the affine line. So at t equals 0, this thing degenerates to a nodal cubic, so it has a singularity. So there is going to be a degeneration of the period mapping for elliptic curves. So the sort of distinguished subspace I of the homology is generated by this class alpha, which is sort of collapsing to a point. So alpha is called the vanishing cycle. And periods against the perp of alpha are remaining finite. So what does it mean to be perpendicular to alpha? Well, roughly it just means that, thinking about, for instance, a curve like beta or some other curve on the Riemann surface, it just means that it's not passing through. So there's like a thinning neck sort of that's pinching. And to be perpendicular to like that cycle is to say that your closed loop that you're integrating your forms against are not passing through that thinning, elongating neck. So, I mean, it makes some intuitive sense maybe that if you are passing through that thin neck, then the periods are blowing up. So that's sort of the picture here. But in this case, the perp of alpha is just the lattice generated by alpha again. And we can normalize our one form so that the integral against alpha is 1. So there's some unique constant c sub t for a given t in a1 minus the origin, for which this integral c sub t times the one form dx over y is 1. And then this integral over beta of that normalized one form I'm just going to call it now a, this is a 1-by-1 matrix, in other words, just a complex number. But I've written a sort of plus z here. The reason why I have a plus z is just that beta isn't really well defined, right? So for instance, I could imagine that instead of this beta, I could sort of do a den twist. And in fact, if I transport this blue beta like in a loop around 0, I'll, the element of the mapping class group is that den twist. So beta isn't really well defined. The period against beta is only well defined up to the period against alpha, which was 1. Okay, and what's happening to this tau sub t is that it's approaching plus I infinity if you've oriented alpha and beta properly. And so in particular, we can build a well-defined number from the period against beta. So beta, the integral against beta isn't well-defined. It's only well-defined up to an integer. But we can take exp of 2 pi I of the period and get a well-defined element of C star. So now I want to describe how this works for genus bigger than 1. Or are there any questions so far? All right, so if not, let's describe how this works for genus bigger than 1. So I'm going to assume that this distinguished subspace I that I mentioned, where periods against I perp are remaining finite, is Lagrangian. In particular, that I perp is equal to I. So this is called sort of a maximally unipotent degeneration. Intuitively, for instance, like if we have a genus G curve and we were considering the Jacobians, we can pinch up to G disjoint cycles, right? But we can't simultaneously pinch more than G disjoint cycles. But I'm going to assume that there are in fact a full G cycles that are being pinched. And that same sort of notion makes sense for abelian varieties in general. And since the psi is Lagrangian and the symplectic group acts transitively on Lagrangians, we may as well just assume that this distinguished isotropic space is the sublattice spanned by the alpha i's. So then there's generalizing this case of embedding the period against beta into C star, there's a sort of Taurus embedding where we can embed the Siegel space into a product of copies of C star. So, so what is this Taurus embedding? It's relatively straightforward. So I mean, these beta I cycles are going to be well defined given this distinguished subspace spanned by the alpha i's. These beta I cycles are well defined up to translation in I. But because we normalized our one form so that the integral against all the alphas were 1 or 0, that means that all of these numbers in this whole period matrix are well defined up to an integer. So we can just exponentiate coordinate-wise every single coordinate. And so we exponentiate each coordinate of the period matrix, and what we get then is a symmetric matrix whose coefficients are elements of C star. So does that make sense? Okay, cool. So now I want to understand, well, how is this period matrix degenerating? And the theorem of Wilfried Schmidt is that the unipotent orbit theorem says that, in fact, if we consider this degeneration as t goes to 0, so this is asymptotic as t goes to 0, then in fact, what is it asymptotic to? It's asymptotic to a co-character of this torus. So what is this? This is a co-character of the torus C star to the G choose 2. So a co-character, by a co-character, I just mean, an inclusion of C star into C star to the G choose 2, which is a composition of a group homomorphism and a translation. So this Cij, you should think of this as this is the sort of translation part. And then if all of theCijs were 1, this really would be just a group homomorphism from C star into C star to the G choose 2. And such a co-character is called a unipotent orbit. And maybe one other thing to remark is that this sort of asymptotic approaching of the coordinate-wise exponential of the period matrix, this is quantified. So there's an explicit speed bound at which it approaches the co-character, and that's all part of Schmidt's theorem. And then the condition that, so we'd like to translate the condition that the original period matrix tau ij was symmetric. Well, we already did symmetric, but had positive definite imaginary part. What does that translate to in terms of the co-character? Well, what it means in the end is that this matrix capital N that I form out of the positive integers Nij is a positive definite symmetric integer matrix now. Okay, so this is an integer matrix, not a complex entry matrix. Right, and intuitively you can think of these Nijs as the sort of speeds, the relative speeds at which a bunch of cycles are collapsing in the abelian variety. Okay, so now what I want to do is I want to say, well, suppose that I do have such a degenerating family of abelian varieties where the period matrix is sort of asymptotically like this. How do I fill in that family at the central fiber t equals 0 in a natural way? So Mumford did some beautiful work on this question, which we'll sort of review now. So let me introduce some notation. I'm going to let P sub G be the space of symmetric integer positive definite matrices. Okay, so P sub G, this is a cone. This is a cone in Z to the G choose 2. It's a cone just because the sum of any two positive definite symmetric matrices is again positive definite and symmetric. So, and I'm going to sort of just get rid of these constants C, I, J, because they just ultimately kind of translate everything just by a, it's just a translation in C star to the G choose 2. So let me just focus specifically on this family of abelian varieties. So this is a family of abelian varieties over, this is a family over, well, it's not really over A1 minus the origin. It's a family over the open unit disk minus the origin. Oops. Move that over. So as you can sort of see, the sort of subgroup generated by these elements of C star to the G is not going to be a discrete subgroup if the absolute value of T is 1, right? But if the absolute value of T is less than 1, then the fact that N has full rank will imply that this is a discrete subgroup isomorphic to Z to the G inside of C star to the G. So by the way, this C star to the G I'm thinking of as C to the G mod Z to the G. So we sort of quotiented by the Z to the G, and now we're quotienting by the tau Z to the G. So yeah, this whole thing is C to the G mod Z to the G mod tau Z to the G. So yeah, the question is, how do I extend this over the puncture T equals 0? So I want to give two answers, one via so-called fans, the fan construction, and the other by the so-called polytope construction. So let's start with the fan construction. And let me just take an example, C star squared mod, the group generated by T squared T and T cubed. So what I want to start off with is a tiling of R to the G mod N of Z to the G. Okay, so in this case, what is the matrix N? N here is the matrix 2, 1, 1, 3. Which I sincerely hope is a positive definite matrix. Well, it's positive determinant. Okay, it looks positive definite to me. Yeah, surely. Okay, so yeah, N of Z to the G is just the lattice generated by the two vectors 2, 1 and 1, 3. Which you can sort of see. Let me zoom in a tiny bit. You can see on the grid paper that the two generators of this parallelogram are 2, 1 and 1, 3. Oh, nice. Positive determinant, positive trace. Amazing. That's going to simplify my life in the future. Thank you, Colleen. Okay, so we take a tiling of this. So first we quotient, in this case, R2 by this lattice, and what we get is a flat real 2 torus, okay? And then we take a polyhedral tiling of that, whose vertices are integer points. And I want this to be periodic. So for instance, I could take this tiling of the fundamental domain that I've drawn, and then just translate it around by N of Z to the G, the sublattice N of Z to the G. And so that's sort of my tiling of and then I take the universal cover. So, I mean, this is what I'm saying here. By sort of translating it around, I get a tiling of R to the G. But I want to think of this R to the G inside of R to the G plus 1 at height 1. So sort of the picture here is that I have I've put something at height 1. I have this tiling of the plane, and then I am sort of putting it height 1 inside of a one-dimensional bigger space, okay? And then I can take the cone over the tiling. So the cone over the tiling is some infinite union of polyhedra. So for instance, if we take a triangle here, the cone over this triangle is going to be a like an affine cone, in R3 generated by 3 vectors, a simplicial cone. And now I take the toric variety of this periodic tiling of the cone over the periodic tiling. And so I have some toric variety, which, is constructed by dualizing each cone and taking spec of that monoid. C adjoin that monoid. And then finally, I quotient by n of z to the g. So I can quotient by this because, so this acts on r to the g at height 1 just by translation, and that action extends to a linear action on the cone over the plane at height 1. So this is a linear action on r to the g plus 1, and it preserves this f tilde, the cone over the tiling. And as such, it then acts on the toric variety of this fan, and I can quotient. So when I do this, I want to sort of observe that this toric variety, the quotient of this toric variety, actually has a map to A1. So what is this map to A1? Well, there's a map from this cone at height 1 just to a positive ray in R, which just sends a point to its height in the last coordinate. And that defines a morphism of fans. So it therefore defines a toric map from, so this map, maybe I can call it, I don't know, phi or something. This defines an induced map to the toric variety associated to the positive line, which is A1. So this is induced by phi. And then since this linear action preserving the plane at height 1 preserves the height function, it preserves the map, and therefore we can descend the map to A1 to the quotient. So this is what I call the fan construction, and it produces a degenerating family of abelian varieties. So if we take a fiber over a non-zero point t in A1 of this x of f tilde, we just get C star to the g, a torus. And this action, this sort of toric action by n of z to the g will then act exactly by translations of this form. And so the fibers over T non-zero are exactly our original family, okay? This is just a way to construct our original family as a certain infinite quotient of a toric variety. But now the nice thing is that this toric variety, it has some toric boundary, and the toric boundary is encoded in the combinatorics of this tiling. And so what we end up getting is that the fiber over 0 is a union. So its dual complex is equal to the original tiling F naught, and it is a, and this is a union. So this is a union of toric varieties. So let me actually just do let me look at this specific example. Okay. So let's see. So how do fans work? Well, the way fans work is that lower dimensional cells correspond to higher dimensional torus orbits. So in this case, you can see that modulo the lattice, there are exactly 3 vertices here, 3 zero cells of the tiling, right? And each one of them is, you can sort of think of as the fan of a toric surface. So I'm going to draw these little arrows. And what I have there is that this black dot here with its arrows pointing out gives the fan of a toric surface. And I just take the toric variety of that toric surface, and then I glue these toric varieties together. So here, who can tell me what is this middle component here? What is that? Do we recognize the fan? Yeah, I see someone mouthing P2. Okay, so yeah, for instance, one of the components here is P2. Here's like a weighted projective plane, and this one has more, right? Because this one is equal to all of these. These are all the same, right? And so we need to sort of locally, we need to kind of glue together to sort of see what structure we have. Okay, so we see the fan of some toric surface there also. And then we glue these toric surfaces by the combinatorics of the picture. All right, so that is the fan version of the Mumford degeneration. It's actually less well known maybe than the polytope version, which I'm going to discuss next, but it's the one which generalizes most easily to K3 surfaces. Okay, so now let me say, what is the polytope construction? So the polytope construction is going to actually build the projective coordinate ring of the degeneration. So let's start by, we have our positive definite integral matrix N. And now let's take all points of the form like, sorry, so this V is supposed to be ranging over, this V is in Z to the G here. I take the norm of every integral vector, and then I'm going to subtract a linear functional in V and divide by 2. So this linear functional, you can think of it, it's just the characteristic vector of the quadratic form n mod 2. So it's chosen so that this numerator is always divisible by 2. And so I get to divide by 2 and I still get an integer point. So this point here is going to be in Z to the G plus 1 because I've chosen L to be the linear functional associated to dotting with a characteristic vector. So going down one dimension, let's just do the simplest one-dimensional case where the quadratic form is n of v equals v squared. So this is the this is just the positive definite matrix 1. And I'm going to take L of v to just be v, so that v squared minus v is always divisible by 2. And now, so I graph the value of this function at every lattice point, and then I take the hull of all of those points. So here I've shown this for this specific example. If you look at these dots at the corner, so there's this sort of discrete parabolic shape, right? And at each corner, I just have the graph of the function v comma v squared minus v over 2. So, you know, the two zeros of v squared minus v over 2 are 0 and 1. So the value is 0 there. And then, you know, it sort of grows quadratically as I go left or right. And then I've taken the hull, so that's Q. So that's this whole interior of this discrete parabola shape. And now, essentially, so first of all, there's an action of z to the g. As before, there's again an action of z to the g on this hull. So what I do is I can translate the z to the g part, and then I need to do a vertical shear. So in this case, if I translate horizontally by 1, then I need to do a unit vertical shear to keep this parabola. So it'll sort of successively move each edge of this parabola. And then I refine the lattice to some order. So in this case, I've done an order 2 refinement of the lattice. And what I do is I take some point and I take its orbit under the z to the g action. Okay, and I sum all the monomials. So I've done this for the point that rests on this edge. So this point associated to the value x equals 1/2 or z equals 1/2, or not z, but maybe I should call it x equals 1/2. And yeah, so I've sort of taken the orbit, and that's given by these various colored dots. And then I just sum all the monomials associated to that orbit in the refined lattice. And that produces a theta function, theta 1/2 of zq. But I can do this in general for any torsion point, of order n in r to the g mod z to the g. So let me call that some vector a, and I have this theta a of z tau, where I just take the orbit of the sort of point a under this z to the g action, and I sum all the monomials. This is a theta function, and I can take the ring over c double bracket t generated, or the monomial, sorry, not the ring, the monoid, what do I mean? The module, that's the word. The module freely generated by these theta functions over c double bracket t, and it turns out there is sort of a multiplication rule. So, theta a times theta b will be some sum of various structure constants, like, I don't know, u, a, b, c, theta, c. Except the one thing to keep in mind is that these structure constants are in this power series ring, c double bracket t. Yeah. By the way, the multiplication, if the denominator is n in one and m in the other, it's n plus m in the product. All right. So in particular, for principally polarized abelian varieties, there's a distinguished ample divisor actually on the fibers of this family X. So maybe I should say this family can be algebraized. So that it's not just over a power series ring, but really over a variety. I'll ignore the potential spam. Okay, so these can be algebraized, and there's a family of divisors on this family of abelian varieties because, well, there's only one torsion point in r to the g mod z to the g, which is the origin, right? And so I can take the theta function of the origin, which is just to sum these sort of monomials here that are appearing at the corners of the thing that we're taking the hull of. Those monomials give what's called the is it called the Riemann theta function? Yeah, this is called the Riemann theta function. And we can take the vanishing locus of that, and that defines some ample divisor on xt, including x naught. So I want to introduce a definition. So given an n in the space of positive definite matrices, I want to declare del of n to be the sort of bending locus of this piecewise linear function. So when we take the hull, this is sort of the overgraph of a piecewise linear function, and that PL function has a bending locus. So in this case, the bending locus is just at, so here we have like r mod z, and the bending locus is only at the point 0 in r mod z. But in general, there's going to be some sort of polyhedral decomposition of r to the g mod z to the g where this PL function bends. And another description of this central fiber when you do this Proj construction is that it's a union of toric surfaces whose now intersection complex is this Delaney decomposition. So this is called the Delaney decomposition. And in fact, not only does it encode the combinatorics, but the loci where this function is linear, those are polytopes of toric varieties. So x naught is the union of like VI, where the polytopes of VI are the cells of the Delaney decomposition. Are there any questions about that? Mumford's construction, very beautiful construction. Okay. So then, if not, then we can sort of now discuss how you sort of extend this just from a one parameter construction to a higher parameter construction. So let me define the second Voronoi fan. It's a decomposition of the space of positive definite G by G integral matrices into subloci where the Delaney decomposition is constant, okay? So, yeah, so somehow PG is itself decomposed into polyhedral cones, where this Delaney is constant. Okay, now I have like a big gigantic chain of families and theorems. Okay, so let me start with the partial quotient of the Ziegel upper half space by the G by G integral matrices. So these are acting by translation. These are acting by translation. Translation on this period matrix tau. So we saw that to kill that translation, we had to take the coordinate-wise exponential, remember? And so there's a family of Abelian varieties, principally polarized Abelian varieties over this quotient, which is to do this exact construction where we take C star to the G modulo E of tau, E being the coordinate-wise exponential. And theorem of Namikawa says that so this embeds into C star to the G choose 2, this is that Taurus embedding. And then we can extend this torus by the toric variety of the second Voronoi fan, of the Voronoi fan, I guess I call it. So this is the toric variety of the Voronoi fan. So I know it's slightly confusing because there's toric varieties appearing on the base, in AG, and there's toric varieties appearing in the fibers. But that's sort of the beauty of the Abelian variety case, is that like the base and fibers have a sort of combined toric description. So we take this extension associated to the second Voronoi fan, and then Namikawa showed that if you do this Mumford type polytope construction, it can actually be done over this toroidal extension of HG mod sim G by G of Z. So this, by the way, this quotient by translation, this is called the first partial quotient in the theory of toroidal compactifications. Okay, and now this toric variety, the second Voronoi fan, it's visibly GLGZ invariant. So how does GLGZ act on the space of positive definite symmetric matrices? It acts by sending n to A transpose NA. Okay, and the Delaney decomposition is invariant under that just because it's just a change of basis of that z to the g, right? So, so that, yeah, the Delaney decomposition is invariant under the GL-GZ action. And so we can quotient this toric variety x of the Voronoi fan by GL-GZ. And then similarly, because the Delaney decomposition, as we said, was invariant, this Mumford polytope construction also descends. And finally, I haven't discussed what you do in a non-maximally unipotent case, but this construction can be extended over the sort of other cells of the Baily-Borel compactification of AG, and you can produce a proper family over this second Voronoi compactification of AG. So it's a theorem of Ash-Mumford-Rapaport-Tai, you know, or maybe not a theorem so much as just their paper is about doing this construction. So once we have this family, we can ask, well, does it solve some sort of moduli problem? And a theorem of Alexeyev from the 90s is that the answer is yes, up to normalization. So if we normalize this, sorry, not that, but AG Voronoi is the normalization of a solution to a moduli problem. And this X bar is the, I should really say, is the pullback to the normalization of the universal family. So what is this moduli problem? It's the moduli of so-called semi-abelic pairs, which I will discuss a tiny bit now, though this is not my area of expertise. So, you know, I will necessarily simplify some things. Okay, so so this is sometimes called a KSBA moduli after Kolar, Shepard, Barron, and Alexeyev. Most recently, because I've been writing papers with Valeri, we call it stable pair moduli. So what is a stable pair? So it consists of two pieces of data, a variety X and a divisor R contained in X, satisfying the following two conditions. First, we need that the canonical bundle of X plus the divisor R is an ample divisor. And the second condition is a sort of singularity condition. It says that the pair X comma R has so-called semi-log canonical singularities. So I'm not going to give a definition of that, but I will give an example. So in the simple case where X is a curve and R is a sum of points, this pair X comma R has SLC singularities if and only if X is a nodal curve, first of all, just, you know, simple nodes. And the points of R have to be distinct non-singular points. That's this SLC singularities condition of the pair. The second condition, this stable, or KX plus R is ample, that just encodes the fact that each genus 0 curve has at least 3 marked points, and each genus 1 curve has at least 1 marked point. So this is with nodes counting, as usual. That is just to say that a KSBA stable pair X comma R is just the same notion as a stable curve. And so the theorem of Kolar, Shepard, Barron, Alexeyev, and now others concerning the projectivity rather than just the properness is that this space of stable pairs is projective. So to be fair, what I really mean is an irreducible component of the space, because there's maybe a countable number of components, but I just want to restrict to like one component. Okay, so because this space of stable pairs or its components are projective, we can take the closure of some locus inside it and get compactifications. So an example would be if we take MGN, smooth genus G curves with n marked points, and we take its closure in the space of stable pairs, we exactly recover the Delaney-Mumford compactification of MGN by stable curves. And so to sort of recall what I was saying about Valeri's theorem about this family solving a moduli problem, we can define AG bar theta to be the closure of the pairs x comma epsilon r, where x is a principally polarized abelian variety, and this r is the unique theta divisor. And now the reason why I chose this epsilon, so this is like a kind of technical issue relating to the fact that this pair has to have SLC singularities. But if you think about it, I mean, it's kind of natural to take a really small coefficient for epsilon. So yeah, maybe I should say a Q divisor here. Okay. So if I take epsilon really small, I still get the condition that kx plus r is ample, right? Because k, the canonical bundle of the abelian variety is trivial. So even an arbitrarily small addition of something ample will make kx plus r ample. So this is maybe a reason why you would sort of expect this epsilon here. And so I can take the closure of the PPAVs with their theta divisor, and this is my definition of this AG bar theta. And sort of the right way maybe to phrase Alexeyev's theorem more precisely is that the second Voronoi compactification of AG is the normalization of this closure in the space of stable pairs. So maybe I should stop there for this lecture, because next time we're going to discuss how to sort of do an analogous thing, but for K3 surfaces, and that seems like a new topic. Yeah, so that's it.
So, okay, let's thank Philip for a nice talk. Now, does anybody have any questions? I could start with a kind of a more general type of question, which is, can you get other compactifications of MGN? There's these R spin curve things and stuff like that.
You mean as a moduli space of stable pairs?
Well, I mean, as a closure inside some kind of thing like that, yeah.
Yeah, I don't know. That's a good question. Like I actually recently realized there is like a supernatural stable pair compactification, which I don't know has been considered. I don't know if it's related to this, but like, let's take the Weierstrass divisor on a curve, right? So this is a divisor of degree like g cubed minus g or something like that, well, for a very general curve, these are all distinct points. But if you take, the stable pair compactification for the Weierstrass divisor, you're gonna have some interesting like blow-ups and things like that of MG and bar when like Weierstrass points collide. I mean, I guess the key question is like for these spin things, like, is there some sort of divisor that kind of associated to it? Like, if you can associate canonically some sort of divisor to one of these compactifications, then that's like a good chance, I feel like, of something that would work. Mm-hmm. So yeah, well, maybe I can ask you a question. So are these compactifications, are they isomorphic to MG on the interior? Or do they blow up the inside of MG?
No, it's the same on the interior, I think.
It's the same on the interior, yeah. So that's kind of tricky because, see, for these stable pair compactifications, oh no, but you can always take like small coefficients. So
isn't stable pair like isn't SLC mean simple normal crossing? Or is that not?
Yeah, but right. Yeah, that's a good point. So you're saying that even away from the divisor, like away from the divisor, you need just like nodal curves. But I mean, I guess, right. So you know that all of the curves in your family, in your universal family, are nodal. But I guess a priori you could still have some sort of blow up maybe of MG and bar. So what you know is that like there will be a stabilization map. So like your stable pair compactification is going to dominate MG and bar, a biomorphism. But that doesn't mean that you can't get a different compactification. Like there might be extra marked points, like for the Weierstrass divisor, you know, you started with just MG, you got this extra divisor for free. Some of those Weierstrass points are mapping into things, into nodes of the stable limit, right? So like to produce a stable pair limit, you'll need to blow up those components. I don't know though, yeah. That's a good question. Maybe you can tell me more about these compactifications at some point. I don't know, like, what are they? Yeah, we could discuss it further after the talk.
But maybe it's, yeah. So do other people have further other questions? Okay, so I'm sure we'll have more questions, I think, after the second talk, which is on Friday. I think I should, if I correctly noted the schedule. Okay, so let's thank Philip for the talk.